Now we use a simple example to understand the statistical properties of the two-stage cluster sampling. In this example, the simple random sampling and simple random sampling design. So simple random sampling in stage 1 and then simple random sampling in stage 2 design will be considered, and then we further assume that the cluster sizes are all equal, so mi are all equal to m. And in this case, the unbiased estimator of the population mean is simply so which is the total divided by capital N. Capital N is Ni times M, and then this is essentially the sample mean. So simple mean. Okay. So the variance of this mean estimator can be obtained by applying the variance formula of the population total. So this one. And note that we already derived this variance formula, right? So so that from here somewhere. So this is the variance formula that we derived. So we can just use this, okay, to get this one. And then note that this guy is what? Ni minus 1 I equal to 1 to capital Ni Ti minus T bar U. And Ti is MIY and M y bar IU, right? And MI is all equal. So we can write it as M square. Okay, so Ti square M square divided by Ni minus 1, and then summation is over y bar IU minus y by U, something like that. And then this one is M times SB square. So that is this one. So that basically this is SSB divided by M minus in the ANOVA table. Similarly, you can check that the second term will be something like this. So that is actually SS within divided by its degree of freedom, mi minus m minus 1. Okay, so this is just the algebra. So the variance expression here, the final variance expression here, is worthy of discussion. The first term, this term, notice that this is just the finite population correction term, so we can you don't have to worry about this much. But this is the variance part divided by sample size. So the sample size is the variance part is the between part between variance, and then sample size is Ni times M. So that's basically the sample size for the single stage cluster sampling, right? So single stage cluster sampling variance term is here, and then second term is essentially the within cluster variation component, and then the sample size is now the Ni, the element, the number of element, right? So Ni times M, small m, so which is the stage 2 sampling part. Okay. Now we use the intra-cluster correlation coefficient to use rho, right? So rho is the so the definition of the rho is like s square. So that is the rho that we learned in last week. And then one result is this. So SB is something like this. So we can use this one. We can use this one and then plug into here, right? To here. So basically, let's write it. Variance of the y bar is, ignoring the sampling fraction, this is ni times m, right? And then plus 1 minus m divided by m, capital M. So m divided by capital M, and then s within square divided by n I times m. So you can use this. So you can use this formula to so that means s square divided by n I m. Then you have n over, so this is a small m. Okay, so n I times m, small m, and then this one becomes a small m divided by m, large M, times SB. SB is 1 minus rho plus m rho plus s square divided by nm times 1 minus m over m. Okay. 1 minus m over m times 1 minus rho. Okay. So that will give you, so you can basically combine, and then in the end you can see that this guy is actually cancels with this times this, right? So and then you have 1 minus rho plus m rho, so which is this one. Okay, so m rho, right? So that implies, and by the way, this guy, the first, is variance of the on the y bar on the simple random sampling of size, sample size is ni times m, right? So variance of a simple random sampling of y bar. Okay, and so that means this is a design effect, and this design effect is now, remember that in the single stage sampling the design effect was like this. Okay, right? That was this is the design effect of a single stage sampling. So single stage sampling is nothing but m equal to m, which is this one, right? So this is more general, but for the special case of single stage sampling we have this result. Okay.